Section 8.1 Sequences. In this section, we define a mathematical tool to catalog individual items in a numerical listing called a sequence, and then we define what we mean by the limit of a sequence. Definition: a sequence is a function whose domain is the set of all non-negative integers and whose range is a subset of the real numbers. Each natural number is associated with a value, and a sequence represents the succession of numbers. So, in informal language, a sequence is a list of numbers. If n is a positive integer, the sequence whose nth term is the number Sn can be written as S1, S2, S3, etc., or more simply, Sn in brackets. The number Sn is called the general term of the sequence, except for the first number. Each number Sn in the sequence has exactly one successor Sn plus 1 and one predecessor Sn minus 1. It is often desirable to examine the behavior of a given sequence at n, as n gets arbitrarily large. We can plot the sequence in two dimensions, as shown in the figure. By looking at the graph, we see that it appears that the terms of the sequence are approaching S. The term of this sequence can also be plotted on a number line. It can be seen that the terms of the sequence are approaching S. In general, if the term of the sequence approaches the number s as n increases without bound, we say that the sequence converges to the limit s and write s equal lim of Sn when n tends to infinity. The notation s equals the limit of Sn when n tends to infinity means that eventually the terms of the sequence Sn can be made as close to s as may be desired by taking n sufficiently large. Note that the number Sn may be practically anywhere at first, but eventually the Sn must cluster near the limiting value s. If the terms of the sequence Sn do not approach any number as n increases without bound, we say that the sequence diverges. For example, the sequence whose terms are 1 over n converges to 0. The idea is that when n becomes large, 1 over n gets small and its value tends to 0. We notice that this limiting behavior is analogous to the continuous case. To find the limit of a sequence, the following tower will be useful. At the bottom of this tower is the logarithmic function. At higher steps are power functions with increasing power. Exponential functions and factorial functions come as subsequent steps. At the top of this tower is the function n to the power of n. Notice that the quotient of two functions at the same level converge to a constant. The quotient of a higher function to a lower one approaches infinity, and the quotient of a lower function to a higher function approaches 0. For example, find the limit of 3n squared plus 4 divided by n squared plus 5n when n tends to infinity. The numerator and the denominator are both polynomials of order 2. The ratio of the highest orders is 3, so the limit is 3. Next, find the limit of 3n cubed plus 4 divided by n squared plus 5n. The numerator is a polynomial of order 3 and the denominator is a polynomial of order 2. So the limit is infinity. The following example illustrates the case where the numerator is a polynomial whose order is less than that of the denominator. Find the limit of 3n squared plus 4 divided by n to the 6th plus 5n. This sequence converges to 0. We consider another example. Find the limit of 3 log n plus 4 divided by n plus 5 square root of n. The numerator includes a logarithmic function and the denominator includes power functions. Since the logarithmic function is at lower step than the power function in the tower of power, this quotient converges to 0. We show one more example to illustrate the usefulness of the tower of power. Find the limit of 5 exponential of n minus n divided by n squared plus 2 square root of n. The numerator involves an exponential function and the denominator involves power functions. Since the exponential function is at higher step than the power function in the tower, its quotient diverges to infinity. Note that the procedure to find the limit of a sequence is very similar to the one we use when we evaluate limits of functions at infinity. The theorem on limits of functions carries over the two sequences. We have the following useful results. Suppose Sn converges to S and Tn converges to T. Then the sum of Sn and Tn is a sequence that converges to S plus T. The product of Sn and a constant k is a sequence that has limit ks. The product of Sn and Tn has limit st, and the quotient of Sn to Tn approaches S divided by T if Tn and T are different from 0. The squeeze rule can be reformulated in terms of sequences. Suppose An is less than or equal to Bn is less than or equal to Cn, and lim of An when n tends to infinity equals lim of Cn when n tends to infinity equals L. Then lim of Bn when n tends to infinity equals L. The proof of this theorem follows the same steps as the proof of the squeeze rule for functions. Now we are going to find the limit of some sequence. The first sequence is 1 plus 1 divided by k to the power of k. Notice that we have k raised to the kth power, so L'Hopital's rules needs to be used. First, we need to take the log of the general term. Log n of 1 plus 1 divided by k to the power of k. By using the power rule for logarithm, it results in the product of k to log n of 1 plus 1 over k. We change the product into a quotient by dividing by k to obtain log n of 1 plus 1 over k divided by 1 over k. Now the limit of this quotient has the indeterminate form 0 by 0. This limit is calculated similarly to the continuous case. Replace k by s, where s is a real number. The limit is calculated by L'Hopital's rule. The derivative of the denominator is minus s to the power of minus 2. The numerator is log n of 1 plus 1 over s, so its derivative is 1 divided by 1 plus 1 over s multiplied by the derivative of 1 plus 1 over s, which is minus s to the power of minus 2. The limit equals to 1 divided by 1 plus 1 over s. When s tends to infinity, it gives the result of 1. So, the limit of log n of 1 plus 1 over k to the power of k equals 1. Remember that we have changed the problem by taking the log. Log of what we want is 1, which implies what we want is exponential of 1. So, the initial limit is e. We consider another example. Again, we change the problem by taking the log. Log n of k to the power of 1 divided by k. Using the power rule for logarithm gives 1 over k multiplied by log n of k, which can be written in the quotient form as log n of k divided by k. By the tower of power, log n k is at lower level than k. Therefore, the limit is 0. Another way to find this limit is to switch to the continuous case, replacing k by a real variable x and using L'Hopital's rule. The limit equals to 0. So the limit of log n of k to the power of 1 over k is 0. Remember that we have changed the problem by taking the log. Log of what we want equals 0, which implies what we want is exponential of 0. The result is 1. So we have proved two important facts. Lim of 1 plus 1 over k to the power of k when k tends to infinity equals e, and lim of k to the power of 1 over k when k tends to infinity equals 1. The second one may be also written as lim of the kth root of k when k tends to infinity equals 1. We introduce some terminology associated with sequence Sn. Sn is increasing if Sn plus 1 is greater than or equal to Sn for all n. Sn is strictly increasing if Sn plus 1 is greater than Sn for all n. Sn is decreasing if Sn plus 1 is less than or equal to Sn for all n. Sn is strictly decreasing if Sn plus 1 is less than Sn for all n. Sn is monotone if it is either increasing or decreasing. Sn is bounded above by m if Sn is less than or equal to m for all n. Sn is bounded below by m if Sn is greater than or equal to m for all n. Sn is bounded if it is bounded both above and below. In general, it is difficult to tell whether a given sequence converges or diverges, but it is easier to make this determination if we know the sequence is monotonic. The bounded monotone convergence theorem tells us the result. An increasing sequence converges if and only if it is bounded above. A decreasing sequence converges if and only if it is bounded below. A monotone sequence converges if and only if it is bounded. The bounded monotone convergence theorem also applies to sequences whose terms are eventually monotonic. That is, it can be shown that the sequence Sn converges if it is bounded, and there exists an integer n such that Sn is monotonic for all n greater than big N. This is the end of section 8.1. Thanks for watching.